So this video is about series and parallel circuits, what goes into them, what makes them up, what are some of their mathematical properties. So the first thing is what makes a circuit. Well, electrons need a path to get from one side of the voltage source to the other. So we're going to consider a battery here. They need a path. There needs to be a wire that connects the two ends. So that's what we need from a circuit. If that wire is broken at any point, or doesn't ever reach back to that other side, it will not be a circuit. Because no electrons are going to be able to flow because there's not enough energy to jump that gap right there. The other key is that charge will only move in one direction. We're going to use direct current, so the charge is only going to go in one way. It's not going to go in the opposite direction if we have multiple pathways. So if we have something like this, okay, charge isn't ever going to go this way and then turn around and go back the other direction. It's only going to go in one direction from one end of the battery to the other. The other thing for our circuit is that the voltage of the power source will be lost over the course of the entire circuit. So if this is a 1.5 volt battery, when we start, means that there's 1.5 volts worth of energy at one end. By the time we get to the other, there's 0. So that means throughout the course of moving through the circuit, we are going to lose 1.5 volts worth of electric potential energy. Kind of think of it as like going up a hill. You're up here, you fall down. Well, you started with the 1.5 volts and now you have 0 by the time you get to the end. Same kind of principle applies here. So here's a pictorial diagram of the whole thing. We have a voltage given by the battery. It's giving charge to cause electrons to start to move through the entire circuit. Okay. At the load, this is a resistance. Okay, that light bulb is converting that energy from the battery into heat and light. Okay, and then we have a switch here, which is going to control whether the electrons can actually flow through the circuit or not. So again, the electrical potential energy is provided by the battery. It's converted into heat and light by the light bulb and the wires inside. And we have a switch that regulates whether or not the circuit's actually completed or not. So the first type of circuit we're going to deal with is a series circuit. So in a series circuit, there's only one pathway for electrons to travel. They're not going to move in different, they don't have options, there's no choices, there's no splitting. Okay, everything's going to flow in one way, which means the charge must move through every component of the circuit. The equivalent resistance of the circuit, meaning if we replaced every resistor with a single resistor, would be the sum of all the individual resistors. And we'll get to that in a little bit, why we need to do that. And the second rule is the current is the same at every point in the circuit. There's no other pathways to go, so the current is going to be the same. Nothing can flow faster or slower because it's all in a loop. And number 5, the voltage of the battery will be equivalent to the voltage drops across every resistor in the circuit. So if we take a look, what does all that look like? Here we have an example circuit. We have 3 resistors in this circuit, and then we have a 12-volt battery source that's going to power things through. So the idea we want to do to figure out things like the current for our circuit is figure out the total resistance for our circuit. And what total resistance means is, what single resistor could I replace every single resistor in my circuit with that would draw the same amount of current from the battery? So in series, it's actually really easy because each of these resistors are going to add to making it harder to get through. They're just going to add to the total resistance of the circuit. So you can think of it as it's like a one-lane road. Okay, it's one road, there's one path to go down, and all we're going to do is keep adding speed bumps all the time, every time we add a resistor, so that car is going to slow down and we'll be able to go as fast. So now, or you think of it as, think about it as like a dam, right? Here's a dam, there's a bunch of water behind it, and we open up one opening in the dam. Okay, and then the current that we get from that opening is going to be based on how big that opening is in the dam. So, and since we only have one pathway, that's what we're limited to, is one opening. Now, one of the things to understand too is when we apply this battery, we're not sending electrons out. We're not saying like one electron here and just racing around. That's not what current is measuring. This whole thing, again, everything is made up of atoms and electrons, right? So basically the whole thing is kind of like a loop. filled with electrons. And all we're going to do when we apply the voltage to it is cause every single one of those electrons to start moving and the charge to move with it. So as that charge is moving through the circuit, okay, it's because all of the electrons are rotating. So you don't think of it more as like a bike chain than shooting out a single electron and sending it through the wire. It's more like initiating the spin on a bike chain. So how do we find our total? Let's figure that out. So for series, again, really simple. We're going to take R1 plus R2 plus R3 because each of these is going to make it harder to get through. So if we have 8 plus 30 plus 10, that's going to give us an equivalent or total resistance of 48 ohms. So if we had a 48 ohm resistance on this 12 volt battery, it would get the same amount of current as these 8 ohm, 30 ohm, and 10 ohm resistors. Okay, so then it comes down to finding I total. Well, I total is pretty easy because, well, it's based off the total voltage divided by that total resistance we just found. So we have a 12 volt battery applied across a 48 ohm resistor, meaning we're going to have a total current of 0.25 amps pushing through this circuit. Now, because there's only one pathway, no thing on a bike chain can go faster than any other part on a bike chain. That means that the current through this series circuit is every point is going to be 0.25 amps. So if I measure the current here, or here, or here, or here, it's all going to be the same because nothing can go faster than anything else. So the current at resistor 1, which is called I1, is also 0.25 amps. At 2, it is also 0.25 amps, and at resistor 3, it is also 0.25 amps. Again, because no electron can go faster than any other electron, the current is the same everywhere. Now, V1 is going to be based off of the current times the resistance, right? Because V equals IR. Well, the current through resistor 1 is 0.25, and the resistance of resistor 1 is 8 ohms. So that means I am going to lose 1/4 of 8, which is 2 volts. V2 would be our 0.25 times 30 ohms, and 1/4 of that would be 7.5 volts. Make that a 5. And again, be the same thing for V3. We have 0.25 times 10 ohms, and that's going to be 2.5 volts. Now, again, we talked about this briefly in the introduction. When we complete an entire loop of our circuit, we are going to lose all the voltage in that circuit. We'll start with plus 12, and we end up with 0. So that means that V1 plus V2 plus V3 should add up to V total. And if we look at that, 2 volts plus 7.5 volts plus 2.5 volts does equal the 12 volt total we were looking for. So series circuits are pretty straightforward. The key there is understanding that the current is never going to change, and the voltage is dependent upon the resistance and then that total current. So finding that total resistance and that total current are the keys for determining a series circuit. So quick summary there. Equivalent resistance is R1 plus R2 plus R3 ... however many R's there are. The total current is the total voltage divided by the total resistance. The individual current is the same as the total current, meaning that I1 equals I2 equals I3 ... Wherever you're measuring the current is going to be the same. The voltage across an individual resistor is going to be equal to the total current times that resistance of that individual resistor. And then the total voltage, again, is going to be equal to the sum of the individual voltages across each resistor. Okay. So now we get into parallel circuits. These get a little bit more complicated. Series circuits are pretty straightforward. Here we have a little bit things are a little bit more complicated because in a parallel circuit, there are multiple pathways for electrons to travel. And the current isn't going to be the same. It's going to move proportionally through the pathways based on their resistance. Since we know I equals V over R, if the pathways have different resistances, there's going to be a different amount of current flowing through each one. So now here's where things get a little tricky mathematically. The equivalent resistance of the circuit will be the reciprocal of the sums or reciprocals of the individual resistors. That sounds super annoying, but what it really means is this. 1 over RT is equal to 1 over R1 plus 1 over R2 dot, 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 dot. Okay? However many resistors there are in each parallel pathway. The voltage drop across each pathway will be the same. We'll get to that in a second, why that happens. And then the sum of the currents in each pathway should be equal to the total current from the battery. So here we have our parallel circuit. We have 3 resistors, a 12 ohm resistor, a 6 ohm resistor, a 4 ohm resistor in parallel with a 12 volt battery. So now comes the point of finding RT. So again, just when we just mentioned, 1 over RT is 1 over R1 plus 1 over R2 plus 1 over R3. So we have 1 over 12 plus 1 over 6 plus 1 over 4. So when we go to solve that, one way to do it is just find a common denominator between the fractions. So this would be 1 over 12 plus 2 over 12 plus 3 over 12 is 1 over R. So that is 6 over 12 is equal to 1 over RT. So that means RT would be 2 ohms. Okay. So now you might notice that RT is actually less than each of the individual resistors. And that seems kind of weird that that would happen, but here's why. So what's been happening is we have this dam, pretend like it's a dam, right? You have this energy behind the dam, you have water. Well, we open up one pathway, that's putting one resistor in, and water starts to flow. Well, now we open up another pathway, because that's what we're really doing. We're adding resistors, we're adding a new path, and water starts to flow. Well, now we got more water flowing because we've got 2 pathways. So we've actually dropped the resistance to water flowing by opening up 2 routes. And then we open up a 3rd route, and our resistance is going to drop even more. So in parallel, RT is always less than the smallest R individual, meaning the total resistance should always be less than your smallest individual resistor. Okay. So if we were to replace that, all 3 of those resistors, finding our equivalent resistance, we would have a 12 volt battery across a single 2 ohm resistor, which means that, again, IT is VT over RT. So we would have our 12 volt battery, but we'd only have 2 ohms of total resistance. So we're going to have 6 amps of current through this circuit in total. So that means if I were to measure the current here, this would be 6 amps. If I were to measure the current here, it would also be 6 amps because that's the total current. But at each of these points right here, that current splits. Some goes this way and some goes that way. And here, some will go down and some will go to the right. So the question becomes, how do we find out those individual currents across each pathway? Well, we know I for I1 should be V1 over R1, according to Ohm's law. This should be V2 over R2, and this should be V3 over R3. The question just becomes, well, we know what R is, what's V? So this is the key when we go back to some of our early notes. We said when we complete a loop, I'm going to erase some of this stuff so it's out of the way. When we complete a loop in a circuit, like that loop, we should lose all the voltage in our battery. In this loop, there is only one resistor right here, that 12 ohm resistor. So that means in that first loop, I'm going to, in that resistor, I have to lose 12 volts worth of energy. My second route I could take is to go through and down through that second resistor and back to the battery. There's another pathway. So that means in that pathway, I am also going to, at that resistor, I am also going to lose 12 volts worth of energy. Again, because we also aren't going to go backwards. Okay? We're not going to go through one and go back through. It's not going to happen. It's going to drive its way around the circuit from one battery to the other without going backwards. Third loop is to go all the way to the outside and down through that resistor. So that means across this resistor, I am also going to have to lose 12 volts worth of energy. So in parallel, the voltage drop across each resistor, across each pathway, is going to be the same as the voltage of the battery, because, well, that's the only resistor, that's the only point of resistance or possible energy loss in that circuit. So V1 should be 12, V2 should also be 12, and V3 should also be 12, meaning that if this is 12 over 12, I have 1 amp of current flowing through that first resistor. If this is 12 over 6 ohms, I'm going to have 2 amps of current flowing through that resistor, and this is 12 volts over 4 ohms, so I will have 3 amps of current flowing through that resistor. So in parallel, the currents are splitting. In a series circuit, the current remain the same, but in parallel, the currents are splitting because, well, we have different paths for them to travel, different roads for them to go. But the key, what you probably notice here is, there might be 6 amps of total current, but if there's 1 amp here, and 2 amps here, and 3 amps here, and all 3 of these merge together here and split off at this, they merge together here and split off at this point, well, guess what? All 3 of those currents are going to add together to get your 6 amps of total current that we expected to get from our equivalent resistance. If we were to measure the current here, if 1 amp had gone down, there would still be 5 amps worth of current going that way, because we have a split of 1 and 5. Here, after these two merge together, we would also have 5 amps of current, because the 1 and the 5 would come together. So in parallel, the current is going to split up and be your summative property, whereas in series, it was the voltage. So quick summary of parallel circuits. Here's our equations again. 1 over RT is 1 over R1 plus R2 plus 1 over R3. The IT is based off that. The total voltage is going to be the same as the voltage drop across each pathway. The current at an individual resistor, and just meaning 1, 2, 3, or 4, is going to be VT over R1, for instance. And the total current should add up to the sum of the individual currents. So a couple of quick comparisons. Current in series is constant, in parallel it splits, which means that parallel is going to draw more current than a series circuit with the same resistors. So even though you'd have the exact same resistors be in a parallel circuit, you're going to take a lot more current from that battery. What it also means, though, is that when we get to voltage, the voltage drop across individual resistors in series adds to the total, whereas the voltage drop across each individual pathway is constant in parallel. So what that would mean, if we put one battery and we had 3 light bulbs in parallel, and then we had one battery with the same 3 light bulbs in series, these, the parallel ones, will be brighter. There is more voltage, and these will be dimmer, assuming this is the same V on the battery, because each of these are going to be minus V, minus V, minus V, and each of these will be minus V over 3, and we'll be using as much. And you're also getting more current through the parallel circuits. So again, powers IV. So if I goes up and V is up, it's way brighter in parallel than it is in series. So there's an advantage. It's also a drawback because you're taking more current. Adding resistors in series increases resistance, okay? Adding resistors in parallel decreases total resistance. Again, you're adding another pathway, so the total resistance goes down. So last quick thing here for series in parallel. In series, so if you have a light bulb strand, so it's kind of a good example. One bulb goes out, the entire strand goes dark. You've broken the circuit, no electrons can move anymore. Which means, because it's in series and you have all those individual resistors, you're going to need more voltage to power every bulb. However, the current is minimized, okay? Because your resistance has gone up, your current will go down and won't use as much current, but you're probably going to need a larger voltage source to make sure every bulb lights up. Another advantage to series is that the amount of wires is reduced because you're just doing one wire from one bulb to the next, right? However, if you set up your light strand in parallel, one bulb goes out, well, the rest of them stay on because they still have their voltage source, they still have their wire connection to the battery. It does require a lot more wire to hook it up, and it's going to draw a lot more current from the same voltage source. However, you don't need as much voltage because each light, again, is going to drop the same voltage as the battery. So if this was a 12-volt battery powering this thing again, we would lose 12 volts there. We would lose 12 volts here. We would lose 12 volts here. Whereas in series, if we had these just 3 light bulbs, each one would lose 4, 4, and 4. So you can see to get them brighter, we would need to up this voltage to get them to that same 12 volt drop. We would need to up the voltage to 36. So there's benefits and drawbacks to both, and we'll kind of explore that some more in class.